A lot of good reasons to harvest rainwater, especially in the arid West, especially in the drought-prone Southwest Four Corners region. And there's also a lot of precedent that it's been a ancient strategy for survival for eons. This particular picture, I don't know if my cursor shows up, but kind of the bottom left, you can see like a rock band, and that was a check dam built hundreds of years ago in northern Arizona, just outside of Flagstaff, to slow down the runoff that was concentrating in these gullies. And a lot of indigenous people used to, and still do, use these techniques of runoff agriculture to grow staple crops and to help to supply for some of their basic needs on an agricultural and plant production standpoint. And also this picture from Mesa Verde, it's a little hard to see, but if you can see my cursor about the top center, there's these black streaks and you can still see a little snow. That runoff would go over this cliff and land in this circular cistern down below. So again, centuries ago, people were harvesting the rain whenever they could as a means of survival, because the alternative was you'd have to find some other surface water source and then haul that water back to where you were living, because that was before the days of municipal water supply systems and wells and some of the other infrastructure and luxuries that we have to also help supply our water needs these days. There's also a lot of precedent throughout the history of our country, not only in the West, but throughout of early settlers setting up barrels and tanks to catch rainwater, and also during the Great Depression, the time of the CCC here, the Civilian Conservation Corps locally in Moab and lots of other places around the country, extensive watershed restoration work occurred. And so this picture here is of a check dam in the Lion's Back kind of sand flats area of Moab, and I've stood in one spot and been able to count at least 35 just in one view, and they've just been done extensively up and down some of these drainages to protect the town from flooding and to catch and hold some of the sediment that's prone to run off these highly erosive hills. And so these same types of strategies and concepts are also very valuable for us, both on our watershed scale and to incorporate into our daily lives and into our home landscapes and the landscapes that we see every day in the communities we live in. Some of the other reasons that water harvesting is important is that it really helps to connect the dots between things. Water is really universal in tying a lot of our infrastructure and our system needs together. And so this was a slide, this is actually Santa Fe, New Mexico's water supply system, not ours. It's a little different in Moab, but not by much. And essentially you have a big reservoir that catches and holds the water. Then that usually has a big concrete, sometimes earthen dam. And then you have pipe works that go to your water treatment plant, that you process that water, make it so that it's up to a potable water quality for human consumption. That takes a lot of energy, a lot of pumps, a lot of chemicals get added depending on the quality of your source water. And then we use the majority of that water that we just put all this energy into to irrigate our landscapes, which in Moab and a lot of the West is 50 to 60% of average residential water use is outdoors, and most of that is landscaping. And then we're looking at another probably somewhere between 15 and 20% of water use being used to flush toilets. So we put in all this infrastructure to then essentially waste that water. It does provide, sanitation needs and green landscapes, but as this picture illustrates, and if you've driven around any town really, the over irrigation, especially of turf landscapes that's just completely wasting water, is a major consumer of our water use. And so by looking at rainwater harvesting, we bring some portion of our water footprint and our water cycle right back into our front yards and right back into our lives where we can see it and watch it. At the same time as all that water supply connections going on, we also have this other phenomena happen on a lot of our landscapes where, because we've graded our land, we've paved it, we've degraded it over grazing, over logging, different suburban development patterns, whatever the underlying issues are, that now when it does rain, it ends up mostly running off, often causing erosion and water quality impairments, and then leaving the upland areas dehydrated. So now the areas that we need the water in these landscaped areas, we now need to tap into that other infrastructure intensive system to bring irrigation water to keep these spaces going, and then trying to mitigate the down gradient issues, whether it's excuse me, flooding or erosion. And that all leads to a whole range of water quality impairments, and different localities have different quality impairments. Here locally in Moab, we have some issues with temperature, and that's partly shading and of the creek, and we also have total dissolved solids and selenium and sometimes E. coli, and all of those can be linked to stormwater runoff. Some of that mineral is naturally occurring, and erosion is a natural process. It's just the scale and the pace of that is something that us humans have drastically increased in many situations. Some other really practical to the homeowner, to the building owner reasons to do water harvesting is to protect your buildings and infrastructure. If you look closely at the foundation of this house here, you can kind of notice that water staining of where water, no gutter, just sheets off. The patio is actually tilted back towards the house, so that water just sits up against the foundation of the house whenever it rains, just causing issues, causing damage. And then nearby, there is a shrub that has died because the irrigation that it was being provided probably wasn't enough, or some other factor. And so if we start to connect these things and start to really look holistically, we can start to say, wow, I can turn this problem of this water causing damage to my building or eroding out the side of my road into an opportunity to put that water into a place where it can soak into the soil and feed the vegetation that we want to have growing. And then there's just all sorts of examples of landscaping practices that work against actual natural system processes and work against hydrological processes. And so these pictures, tattered landscape fabric that inhibits good infiltration and eventually just turns into a pile of trash in somebody's landscape, and pooling of over irrigation and runoff right at the base of trees that could cause them to rot out. So in general, unless it's a tree that's adapted, like a cottonwood or a willow, to have standing water right up against its trunk, we generally want to keep the root crown right where the tree comes out of the soil and starts to become the trunk. We want that to stay high and dry, and then we want that water to be where the roots of the tree can just tap into it, so we're not damaging our landscape. And so there's this study done in Santa Monica some years ago now that essentially had two landscapes of the same size side by side, and they tracked over a number of years how much water that each used, how much yard waste, and how much maintenance. And as you can see from this chart, the amount of water is way less, about 17%. The yard waste, if it's planted properly, you shouldn't still have that much yard waste. There's always clippings and stuff to take out, but I'm thinking that maybe it was overplanted a little bit, resulting in some extra pruning, but then also way less maintenance hours. So again, these systems do take maintenance, but it's less maintenance, and you start getting more multifunctional returns as your landscape matures and starts to work with these hydrological processes. So now I'm going to just jump into some examples of each of these types of systems. I'll go through some of the passive systems, the rain gardens and landscape approaches first, and then talk about some of the technical considerations and best management practices for roof catchment. And the reason I do it that way is that, by and large, having good, healthy soil that is sponge-like and can hold and retain that moisture is your cheapest and largest storage source. So I always encourage people to like first start looking at how can you shape your landscape to make best use and hold that water that's coming to it. And then if you still need more supplemental water, or if you have additional goals that require a cistern or a barrel, then start looking at those, because we always got to remember that everything we do when we're working with water, we have to plan for an overflow. No matter how big you build something, at some point it might overflow, and you need to choose the pathway for that water to go so that it doesn't choose the path of least resistance and potentially cause harm. So on this rain tank, you can see coming off the top left of the tank is that red pipe, and that's the overflow, and that pipe actually then goes into a series of passive rain gardens along the edge of the street. So for both systems and for integrated water harvesting in general, you really want to start with a sense of place. Where are you? What are you working with? Because that's really going to drive what some of your opportunities are and what some of your other design considerations are going to turn into. So it really starts with climate. What's your patterns of precipitation? What's your annual rainfall? How is it distributed over the seasons? What's your peak rainfall intensity, or the most you would typically expect in a, the engineers would call it the 100-year storm. And so we want to know some of this information from a water perspective, along with all of the other climate-based gardening info of climate zones, first and last frost dates, those sorts of things. But from a water harvesting, we're really starting to look at, when does water come to me free from the sky that I might be able to put into use and work within my landscape? And then the other huge layer is your site. What are your specific site conditions that you're working with? Where is your sources of runoff related to your gardens? How much water do you need? What type of plants do you currently have, and what type of plants do you want to have, and how much water do those need? And so as we start to look at some of these together, and that site assessment also starts to look at, what are your soils like? If you have heavy clay soils, you might want to do stuff that's has a shallower ponding depth and is spread out over a wider area, versus if you have a loamy soil, you can fill it up more and it'll soak in a reasonable time frame. And then it's, what are you trying to accomplish? What are your intended uses or functions of this? Are you trying to protect your house? Are you required by the permit process to do some level of stormwater management? Are you trying to have a backup water supply? Are you trying to have as resilient and self-reliant of a water and food production site as possible? So really kind of getting clear on, what are your goals within the context of your site and your climate. And as a general rule of thumb, these passive water harvesting techniques, rain gardens, swales, those things are really best suited for perennials, the plants that live multiple years. You can do annuals, and like the Three Sisters Guild is a classic example of corns, beans, squash plants that have been grown off of rainwater harvesting for centuries and centuries, and it works. It's just sometimes the timing doesn't always work out, and so by and large, especially in your own landscape, putting that passive water harvesting to your perennials is in general the preferred strategy. Gray water is also ideal for perennials and fruit trees, stuff that you're not going to be ripping up the roots, and that can handle the nutrient load of the gray water, those sorts of things. And then cisterns, your rain catchment tanks and barrels, those are generally going to be what you use for a supplemental water supply for some higher water need perennials, or for some annual beds, or to have a emergency supply. So those are just kind of, as we start to hone in on, like, how do I decide, of all these techniques we're going to talk about, how do we start to pick which ones are appropriate for a specific site and a specific person or project's goals? And once we've worked through some of these higher level things, then it's time to start thinking about the specific system components and configurations. How do we actually put these pieces together so that they work, they protect water quality, they protect health and safety, and that they're delivering the functions that we're going for. Like I said, everything requires maintenance and generally has some level of operation or really stewardship interaction to keep them optimal. So you want to think about that and what sort of maintenance your particular system might need. So for example, a roof catchment system located under a locust tree is going to be a lot more work to clean your pre-filters and your gutters than a rainwater catchment system located out in the open, as just one example. And then of course budget, time and money of how much do the different options cost and what are you working with. And a lot of times this stuff gets implemented incrementally, thought through, integrative to have the big picture and to work out how the pieces are going to work together. And then from that big picture say, okay, this year I can do phase 1, next year I'll do phase 2, and so on as budget and time allows. So one of the key principles or concepts that I start with thinking about this stuff is the concept of a watershed. So at its classic definition, a watershed is a geographic area that drains to a common place, usually a river, an estuary, a bay, a lake, the ocean, something like that. For the sake of water harvesting on our own properties and in our communities, we can really start looking at the sub-watersheds or the watersheds of a roof or our site, and that really helps us to hone in on, as these red arrows show, each place you have a downspout, there's a certain area of roof running to that downspout, and we'll get to do a tiny bit of math here in a second. To calculate, we can say, oh, on this downspout A, in a 1-inch rain event, I get 500 gallons, and that information goes into how I size my tank and or my earthworks. And then on the other downspout, oh, that one gets about 400 gallons. And so we can start to break up our properties into these little drainage areas so that we can develop appropriate strategies for each watershed of our roof, or each watershed of our site, and start to match our sources of runoff, our roofs, our driveways, our steep slopes, any of those things, to our sources of, I usually call them our sinks, our places that we need that water. Where can we direct water from that's running off of point A and send it over to where we need it in the landscape.
Jeff, a question from a participant. What if there's no rain gutters or downspouts on the house? This is the case with my house, so I think this is a great question.
Yeah, totally. So there's pros and cons to that. So that would be what we would generally refer to as sheet flow, meaning that that water comes evenly off the entire length of that roof area. If you look closely, there's probably a splash area that might be a little bit indented and might have a little bit more rock showing right where that water comes off the roof and hits the ground, depending on what it lands on. So some of the strategies can be, first, there's the consideration of, is it worth putting a gutter on? Like, do you want to concentrate that water someplace that you can channel it to? There's also ways you can shape the splash area that that water is landing on. I've seen people shape it and essentially put in a French drain type of thing, or like even just a surface contouring. So when that water lands there, it starts moving in the direction that you want it. And that, of course, assumes that there's some slope. So the flatter your property is, the more challenging getting some of the elevations right are to move that water. From a soil erosion standpoint, if guttering's not an option or not desired, you can even just a layer of gravel, something to break up the impact of the raindrops so that they're not breaking apart your your soil and causing it to splash on your house possibly, and then run off and erode. And so those are kind of the range of considerations, and there's no one right answer. It really needs to be thought of in relation to what else do you have going on there, and how much time and resources can you invest in this, and where do you want to use that. But so yeah, from simplest is just a very light shaping of that soil surface and covering it with some gravel or even some wood chip mulch to absorb the impacts of the raindrops, and letting it build up a little bit and then start moving away from the building to a better area. So here's probably the funnest slide of the whole presentation. It's the one where we get to do math. I put this up because in a lot of ways, being able to quantify how much water, and these are estimates, it's not an exact science. The math is actually pretty exact in terms of converting to volumes, but the rainfalls that you receive in a given storm, and how quickly they come, or whether they come in multiple pulses, all that sort of stuff is going to be a lot more variable. But this can give you a sense of, and it holds true for any surface, whether it's your roof, your driveway, your garden, the parking lot next door. You can use this to get an estimate of how much water you can reasonably expect from that surface in different size rain events and over the course of the average rain year. And so the formula is pretty straightforward. It's the area, so in square feet, so that's just your length times your width. For a house, even, you've got sloped roof, but you'd be as if you're looking down just at the footprint of it, because that rain generally is falling pretty straight down. Of course, the wind blows it and stuff too, but for the purposes of this calculation, it's the bird's eye view footprint of the surface in square feet times the inches of rain you want to solve for. I usually start with 1 inch of rain because it's easy math and it gives us a good sense. From a design standpoint, you may look to your city or county stormwater folks in engineering and see what they use as the quote design storm event, and that is what might be required if you're doing a project that triggers permits and there's a regulatory requirement to manage stormwater on site. That's generally based on the 100-year design storm event, or sometimes the 10-year design storm event. And here in Moab, that's 1.74 inches for the 10-year design storm event and like 2.8 for the 100-year. And so, it depends on what your goal and what your regulatory requirements are. But if we go back to this formula, just plugging in 1 inch of rain, that 0.623, that is a constant that converts inches per square foot into gallons. And so feel free to ask me offline if you're really into math and want to know how that got there, but otherwise just trust that that's a constant. And so you fill in those 3 initial variables and we get 1,000 square feet times 1 inch of rain times 0.623 means if we're 100% efficient, we can get 623 gallons of water off of 1,000 square foot roof in a 1 inch rain event. Here in Moab, our average is just about 9 inches. So for every 1,000 square feet every 1,000 square feet in the Moab area, 5,607 gallons on average are landing on that surface. Of course, nothing is completely 100% efficient. So there's different tables that you can look at for, it's called the runoff coefficient. And that depends on your surface area. Like a metal roof probably runs off maybe 98%, 95 to 98% of the water falls on it. Whereas a asphalt shingle roof that has just more texture, more stuff to hold on to some portion of that water, might be more in the 80 to 90% efficiency. So that's a judgment call. I usually use between 80 and 90% efficiency as my assumption, but it depends on materials, roof slopes, overhanging vegetation, some of those other variables. But on average, factoring for efficiency, we're looking at just over 5,000 gallons of water available per every 1,000 square feet. And so that adds up to quite a bit of water over the size of a town. So now to look at in a little bit more detail some of the different techniques that fall under this passive category, this earthworks, rain gardens category. And I'd refer everybody, if they want, I think probably the most comprehensive resource and work out there is Brad Lancaster's Rainwater Harvesting for Drylands, volumes 1 and 2. I listed 2 here because it gets into a little bit more of the technical details, whereas the version volume 1's a little bit more of the theory and principles and bigger picture of stuff, but they're both incredibly good reads. And then I would also recommend people look at some of the stuff that the Watershed Management Group has. They're out of Tucson, Arizona, and they've been doing a huge amount of work and innovation in these fields for a bunch of years now. So above the line, basins, berms, swales, terraces, and we could think of some other terms that would fit in this technique list too, but those essentially refer to different ways of physically shaping the land to be able to hold on to some amount of water. And then below the line, the healthy soils, mulch, and vegetation, those are really the biological components that end up driving the system and making it function properly over time. And really a primary goal of all of this is to build healthy soils and to turning as much of your landscape into a sponge that can soak up, hold on to, and slowly release that moisture and any associated nutrients over time. And then mulch is essential for both helping to feed the soil. It's good for weed suppression, and it also helps to minimize evaporative losses, meaning as the sun and the wind go over a soil surface or pass through plants, that some amount of water is lost through that. And then your vegetation, really having the right plant in the right place and striving to get 100% vegetation and mulch cover of desired things as a primary strategy to outcompeting any weedy species or species that are less desirable to you. And those all work in tandem as you build healthy soils and you continue to mulch and build up that healthy soil, and then you get vegetation with its roots going down in there. That all helps to increase what's called your soil structure that allows for pore spaces where water and air and macro and micro invertebrates and arthropods can all move deeper into the soil. And so the deeper we can get our plant roots and the deeper we can get the moisture, the more resilient our plants are, because there's more soil volume and more soil volume holding moisture for those plants to draw from in times of drought or times in between irrigation cycles, rain cycles, those sorts of things. So to go through kind of, I call it the anatomy of passive water harvesting earthworks. These will look different on each site, but the components are all the same. You really start with a catchment area. In this case, it's a gravel driveway that you can see was starting to erode, starting to channelize a little bit, and all that water had been just running straight down the site and off the property. And so you start with a catchment area, your roof, your driveway, whatever, and then you have some sort of conveyance, whether in this case it's essentially a little speed bump that intercepts the water and channels it over to the landscape. On a house, that would be your gutter and your downspouts. In a gray water system, that would be your piping, your distribution piping. So you have some way to get the water that's landing on your catchment area and convey or move it into your water harvesting area. And so whenever we have this moving water, especially once it's starting to be channelized, it has erosive power, and we want to make sure that we're not causing erosion to our system. And so it's highly recommended to have some sort of armoring. Rocks, cobbles, stuff like that is what I use most typically, but there's other options to stabilize that soil. So essentially, as that water leaves the conveyance and enters your landscaped area, it's not prone to erode out the soils there. And you want to use that same concept of armoring at your overflow too, because again, your water's coming in, you have your basin or your rain garden, your swale in the center that has some amount of holding capacity, and that's going to be the physical volume of water that it takes to fill up that whole space before it overflows. And then your soils will have some infiltration rate, from sandy soils being extremely high to clay soils being very low. And those two together will determine how much water actually soaks in and contributes to your localized soil moisture there. And as I said, you always plan for an overflow. There's inevitably going to be a rain event that's bigger than what your holding capacity is. And so these work really great in series, or we often call them treatment trains, where one overflows to the next, overflows to the next, overflows to the next, and you maximize the volume of water that you can safely hold and the time that that water spends on your site, so it has as much time as possible to soak into the soil. And then, of course, there's the vegetation, mulch, compost tea, all these things that we can do to build up good, healthy soil and get the plants that we want growing. And so this was a project from, maybe almost 10 years ago now in Northern California, and I did all the annotations, so I've just kept it. It works pretty good. But there it is in November, and then the following summer, after a wet California Mediterranean winter, so different in each climate, but we've had similar results to this here in Moab. We just typically need to provide more supplemental irrigation than in some of the wetter climates. But that's kind of the premise. And then the species we choose is really up to the individual designer and property owner. My preference is often multifunctional stuff, ideally things that I can eat or get culinary or medicinal herbs from, and then also tons of flowers and pollinator plants. And it's nice to put in shrub thickets for bird habitat and really start to turn our landscape into both part of our infrastructure, but also an ecosystem of itself. And it's, as we get more of these distributed capacity water harvesting ecosystems, we can really start to have cumulative positive impacts at a neighborhood or a community scale in terms of things like drought resilience, pollinator habitat, food production, stormwater management from quality, localized flooding, these different issues that a lot of communities and neighborhoods faced. And not that this is a silver bullet and will solve all of those every time, all the time, but it's a major part of our packet of solutions. So here's another, a basin or a rain garden. And really what we're looking at here is it's just a shallow, kind of a divot in the landscape that allows a certain volume of water to pool up before overflowing. And so in this case, kind of in the center right where my cursor is where it would overflow, and it'd be able to fill up that entire basin area. With this one, I think had maybe 4 or 5 inches of capacity that it could fill up before it would overflow and run off into the parking lot, which in this case was where 100% of the water was going prior to the rain garden being installed. There was an interesting study came out 10 years ago now from the USGS, US Geological Survey up in Wisconsin, looking at rain gardens. And what they found in this is that your infiltration rate increases over time, including in clay soils. And that's kind of what I was talking about with building soil structure, getting plant roots in there, helping that water soak in deeper so that the biology, both the soil biology and the plant roots, can then go start to work with those soils to improve their structure and their infiltration rates. They found that properly sized rain gardens could handle a catchment area or a contributing area or 5 to 10 times as big. So if you think of that in Moab, if we just use 5 times as big, so if we get 9 inches on average, but you have 5 times the area going into your garden, you effectively are getting 45 inches of rainfall. And of course, the spacing and the sequencing and how much like soaks in and overflows. But the point being is we have a huge opportunity to create little oasis zones and zones of increased localized soil moisture by concentrating and maximizing the use of runoff off of our impervious surfaces and matching it to areas where it can help to support our landscape plantings. They were looking at, in this study, prairie vegetation versus turf grass, and they found that generally prairie vegetation uses less water, so more goes into the soil. And that I think the fascinating part that's not that surprising, but is cool to see them quantify it, is that perennial prairie vegetation roots reach 10 times deeper than the turf grass. And so that means you have all of that life and that ability going down 4.5 feet instead of a 1/2 foot. And so that's really essential for healthy plants, but that's also really key for pulling carbon out of the atmosphere through plant photosynthetic processes and having them release that to form stable soil carbon in our soils. That's beneficial to our plants, it's beneficial to our soils, and it's beneficial to us because it helps start to shift some of that carbon balance. So then there's berms. So that's kind of where a basin is, you're indenting into the ground. A berm is you're building up off of the surface of the ground. And where those come in is sometimes you just don't want to dig. Sometimes you have root systems or infrastructure or shallow bedrock or some number of reasons that you may not want to dig down, but you still want the function of being able to create a physical structure that causes some amount of water to pool up and soak into the soil. It can also be very useful if you're trying to get some additional plant height to create a windbreak, in terms of creating a windbreak or a privacy berm. Sometimes it's nice to get 1 foot or 2 or 4 feet of earthen berm up to then put your plants on top of, so that they start up higher and it takes less time for them to provide some of those other windbreak privacy functions. This particular set of pictures is a colleague of mine in New Mexico, Christian Miley, and he has been doing pinyon juniper thinning and re-veg for a number of years. And what he's come up with is he does the thinning for both for forest health and for fire hazard reduction, chips that material, and then makes these approximately 1 foot high, 1 foot wide berms on contour with the wood chips. And these would be in areas where it's low flow energy. You wouldn't just go stick a pile of wood chips in like a gully that, you know, is subject to flash floods or anything with perennial flows or anything like that. But for an upland situation where you're just having some runoff and water sheet flowing off and not sticking around, these types of berms can be really cheap and easy to put in and highly effective. And the bottom right picture shows that after a few storm events, all the sediment kind of embedded and caked into the wood chips, and it became this really super stable feature that was holding a lot of moisture and starting to rot and have all that good biology going in there. Berms can also be created just, you know, wood chips with soil, with logs or brush covered with wood chips or soil. You can mimic berms by using rocks on contour, which I think my next picture might be of. And so there's a lot of different materials you can use to create your berms depending on what you have available. And so yeah, here's a picture of a rock structure. We call these media lunas because of the shape. Is kind of a half moon shape, and they're actually surveyed in so that the whole central part of the structure is all level and on contour, and then the outer ends are a little bit higher, so as that water comes, it would spread out the whole length of my fingers and then overflow evenly and sheet out into the landscape. And having those ends higher makes it so that that water doesn't come and then just erode out around the edge of the structure. And you can kind of see the little seedlings and the organic debris that got accumulated in the center of that rock structure there.
We have a couple questions, Jeff. One question related to this slide is, how can I figure out my land contour? Good
question. So there's a range of different surveying and leveling tools. I think if you're just looking for a contour, you can use what's called an A-frame, and that, I don't have a resource offhand, but I think if you Googled it, you'd come up with some good how-to videos, and that's good. It's essentially makes an A and has a bob hanging down in the center, and when the two legs are at level spots, the bob hangs exactly in the center, and you make a little mark there so that you can go along the slope or contour of your land and mark that out pretty quick and easily. There's another tool called a water level, where you essentially have two measuring sticks with a clear tube strung between it, and then you fill that tube with water, and two people go and you put the sticks on different spots, and depending on the relative elevation of the water in the tube, you can say, oh, my spot is 2 inches higher than yours, and you can use that to survey. And those are kind of the more like, you can go to the hardware store, buy a couple parts, and like make something pretty easily yourself. And then kind of getting up on the little bit more cost to get, but maybe a little bit more accuracy, but it would be like a laser level. And that's what I use at this point, because I have one and one person can operate it, and it's essentially a laser that sits on a tripod and spins in 360 degrees, and then you can use a rod and go and take your measurement elevations. And that's really useful for larger areas or places with a lot more variation, because you can cover that ground quicker than trying to stretch a 20-foot piece of tubing between, the water level. So it kind of depends on what you need, but I'd say those are 3 good strategies that you could look into.
Another question was, can you talk about the pros and cons of landscape cloth in terms of water retention?
Yes. So if you get a landscape cloth, it depends. They all come in different weaves and different tightnesses. And some people use just plastic sheeting as landscape cloth, and that would not allow any water through. And then depending on the weave of your landscape fabric, some of that water is going to soak through the fabric itself. So I think from a infiltration standpoint, it generally is going to slow it down a bit. The bigger challenge with landscape cloth is that it disconnects the surface mulch from the soil, so you're not necessarily getting that active decomposition to build up good healthy soil over time. It also has been my experience that almost inevitably enough windblown dust and seeds land on top of the landscape cloth that within a handful of years you have weeds and or other plants growing down through the landscape cloth, and then when you go to pull them, you start pulling apart the landscape fabric or the landscape cloth. And so I generally don't use any landscape cloth. I use it on some watershed restoration structures where you don't want the water to pipe through, and that's beyond this. And like, I would maybe use it under certain paths or patios, but knowing that plants will start to colonize on top of it. And once you start pulling it out of there, I've just seen a lot of really messy landscape cloth, and it's really hard to get out of there once it's in, because it just starts getting embedded in everything. And so my preferred method is a thick sheet mulch, where you can accomplish something similar, but you're working with the decomposition process. And that is, you lay down sheets of cardboard. You can use newspaper or other stuff with a good overlap, usually 6 inches or more, to smother out any seeds and any weeds that are currently there. And then you add at least 4 inches of wood chip mulch, usually 6 or more in cases. And then that'll act to smother out the current seed banks. And it's usually, you get anywhere from 2 to 3 years before that's broken down enough that seeds can start germinating on top, but it's helping to feed. That's often a very good strategy around perennial trees, shrubs, other stuff, that you're giving it that one up of weed suppression combined with building soil and retaining soil moisture to help advance the plant growth of the stuff that you do want there, so that over a course of a number of years, you can shift the plant community from what might have started as annual noxious weeds, you know, the cheat grasses and kochia and stuff, and start pushing that towards the desired vegetation. But it is a ongoing process. And so a little off the question, but I just had to get my say in on landscape cloth there. And then this is a swale. This is at Occidental Arts and Ecology Center, and a swale is, in permaculture terms, it's an uncompacted ditch on contour. And so that goes back to that previous question of like finding the contour. If you are familiar with topographic maps, each one of those little lines is a contour, meaning a level spot across the landscape. And what the premise of the swale is that it intercepts water that's being concentrated in one spot and spreads it evenly out over a given length of the landscape before it overflows, and in this case goes into the next swale that's just down gradient of it, and it gives all of that water time to soak into the ground and support the nearby vegetation. And then terraces are another good strategy. They're most appropriate for harvesting direct rainfall. If your terraces are big enough, robust enough, and you shape them properly, you can direct roof runoff or, you know, some other patio runoff onto a terrace. But you just have to use a lot more precaution and make sure that they're built right and all of that. So I generally recommend that to start, think of terraces as essentially catching the water that's landing on that specific spot and keeping it from running off, and providing yourself with some flat spaces to plant from. And then this picture also shows a broken up concrete patio, what we often call urbanite, and that's another form of passive water harvesting, is to have some of your infrastructure, patios, driveways, to be permeable so that some of the water that's falling on them can soak through the cracks into the ground there instead of running off. So that's another option for situations where you want a hardscape feature, but you don't want to have to manage the runoff somewhere else by, so you put in something that has some gaps and spaces in it. So kind of a summary here of some of the key considerations for passive earthworks is really looking at your infiltration capacity of your soils. You don't want water to stay around so long that you can grow mosquitoes. So generally you want your earthworks to be infiltrating completely within 2 days, 3 at the most. 1 is even better, but that 1 to 3 day range, because it will help to prevent mosquitoes and get that soil in. To do that, you need to be building healthy living soils and getting the right plants in the right place to help support those soils. As you're digging basins or making berms, if you have walls that are beyond kind of the natural angle of repose, then they're going to need some sort of armoring, some sort of terracing, rocks, something to keep them so they're not just sloughing off and running off too much on you. You really want to pay attention to protecting infrastructure. So that's keeping these retention basins and these rain gardens at least 10 feet away from the foundation of your building, so that water doesn't cause saturation and have impacts on your foundation. And then it's also making sure that you're not inundating vegetation or something else that doesn't want to have standing water around it. So it's really kind of paying attention to where your ponding is going to be. As you think about your basin depth and that volume, you want to also account for that over time you'll be adding mulch, it'll be breaking down. Some amount of sedimentation might be getting in depending on where your runoff is coming from. A roof's going to have a lot less sediment than a gravel driveway, so depending on your source, you might want to have an initial smaller basin that lets some of that coarser sediment fall out before overflowing, so you can plan to go and maintain it every couple years or after each big storm or whatever is needed based on your specific circumstances. And then always provide an adequate overflow, and then call DigSafe, which is the 811 number, and that's required, so they'll come and locate underground utilities, and that's best to do early in the design, so you know, oh, there's a gas line there, or the power line goes there, and you have that knowledge as you start to design and decide what you're doing.
We have a couple more questions.
All right.
So one of the questions is, if there is soil erosion around the house structure, should I just add the small gravel on top, or should I add soil there and then gravel?
Honestly, that depends on your finish grade. In general, you'll have like the baseboards of your house, whatever stem wall or concrete footer, and you usually want about 6 inches, 4 to 6 inches between your soil grade and the bottom of like the trim of your, or like the walls of your house. So it kind of depends on where you are in that. If you're a foot low, then yeah, bring it back up. But if your grade started out high, then it might even be that you carve a little bit more away and then put down the gravel. So it depends, but that like 6 inch gap from finish soil grade to bottom of house is a pretty good rule of thumb for deciding on that one.
And then another question, do you put the berm or swale on the high point or the low point? So finding the level spot all the way across, is that correct?
Yeah, good question. So essentially you want your berm, or berm, and then your water harvesting, it could be a swale if it's below grade, but the bulk of the earth is going to be on the downhill side. Your water harvesting that you want level is going to be just up from that, and then you want the top of your berm, or like usually when you dig a swale, you're creating a little berm on the downhill side with that dugout material. So those kind of go, it's often referred to basins and berms, because you sort of got to do something with the soil. So it usually ends up being that if you're digging, you just mound up a little bit there, and you want to make sure that your berm is higher than your max water fill line, and then you set your overflow elevation so that the water can fill up here and overflow, and you want a good 4 inches of what's called freeboard on your berm or the downhill side of your swale. So when it's at full capacity, it's overflowing over your rocks, and the whole rest of your berm, you still got a nice lip so that you don't have a blowout somewhere that could mean that all of a sudden your whole swale is draining towards your neighbor's house or someplace that you don't want it to go. So those are kind of those key elevations, is making sure from your overflow height, you have 4 inches of freeboard around the entire rest of your berm. And then from your over height down determines how much volume of water you can hold in that earthwork. And general rule of thumb is that you want, well, it depends, but I often target 6 inches of capacity. But again, if you have clay soils, you might want way less. And if you have sandy soils or a lot of runoff, you might go for a deeper ponding volume. So yeah, and so this next slide is actually a pretty common failure of systems. This is one of the CCC check dams up outside of Moab, and you can see where my cursor is. The rocks, they were all like pretty much level, a little bit higher on this side, but they weren't brought up high enough on the left-hand side. So after some years, and this all filled with sediment, started to even get some native re-veg in it, a rain event came, and instead of going over the stable structure, it was up high enough that it went into the bank and eroded out the unstable soils next to the structure. And now you go up there and it's as if the structure is not doing anything. The water is just going right around it and has carved back down to the original grade that the structure was set at. So when you're doing your overflows and your armoring, it's really important to have them level, and then at least 4 inches, better 6 inches or even more higher on the side, so that you make sure that that water goes over your rock armored overflow and doesn't have this kind of wraparound blowout effect that can undermine the integrity of your structure. And then just some other maintenance things to consider is this is just really, it's kind of the same type of maintenance as typical storm drainage infrastructure. Here in the top left photo, you can see that there's leaves clogging it and there's a bunch of sediment that's accumulated. So depending on where your runoff's coming from, you may also have sediment and leaf debris to clear out on occasion. And then the bottom right is kind of that same wraparound phenomena where these rocks really need to be going up each side of these each side of the swales to get the water to go over them. You can see in that closest one, it's already starting to wrap around the right side. And so luckily we caught that before it did any damage and just added a few more rocks and it was fine. So then there's also just some challenging site conditions where it may not be appropriate to do passive water harvesting. And that could be really steep and unstable slopes. If you're in an area that has dissolvable soils that could, form a sinkhole, or expansive soils that could cause some shifting. Areas with really high groundwater within a couple feet of the surface, there just might not be enough soil volume to soak that water in before it hits the groundwater. Same with shallow bedrock or a low permeability area. Areas of heavy compaction, that's a little bit easier with a machine, or if it's small enough, a broad fork, you can loosen some of that, but it's just something that poses a little extra challenge. And then polluted areas and brown fields, if we don't want to add a bunch of soil onto polluted, or add a bunch of water onto polluted soils and potentially push that pollution down into an aquatic system. So just some things to keep in mind. There's just a picture of a curb cut with some pretty dirty looking stormwater running into it. And then here's a property I've been working on outside of Moab for the past, I think this is year 6 now, 5 or 6. And when I started working there, they had in this top left picture a 100% code approved, engineered, designed and stamped detention basin that was sized to meet the needs of the site, and is essentially this big old pit in the ground with a emergency spillway, and you can't quite see it in the picture, but there's an 8-inch pipe that goes out the bottom, and that pipe drains, if you look at the bottom right picture, so all the runoff from this barn and some of the gravel utility areas around it would go into this basin, and it would come out the 8-inch pipe, and it was carving this gully straight down the middle of the property after just a couple seasons. And then it was going over this big embankment down to the creek, which was starting to head cut and really blow things apart. And so I got brought in to see what we could do from a permaculture perspective. And what we came up with was, it's hard to see in this picture, the next one will show it a little bit better, but this is that same angle. We were able to get code approval and have that same engineer stamp the distributed basins that I put in here to show that they had the same volume, and this organization was able to fill in that big detention basin and start to use it as part of their activity areas for the groups they have here. And we were able to start to re-veg and manage that stormwater. Sorry, I had a slide. And so this is an aerial view of that site. And the bottom is that big gravel thing. That was the detention pond. And now essentially what you see is all the gravel in the circular spots are high and dry paths and teepee pads, so that when they have groups camping out, everybody's high and dry out of the runoff. And then the entire rest of the site, pretty much, that kind of has that greenish brownish tint, those are a whole series of basins and swales that all overflow one to the next. And so where the water used to follow this path here and just shoot straight down and go over this embankment and causing that big gully, now any water goes through here, pools up, soaks in, goes under a bridge, pools up, goes here. And then here, instead of going that way, we graded it so it actually flows this way and wraps all the way around, and then it actually goes off the screen and eventually goes down a stable return, basically down to the level of the creek. So now it's the majority of the water that falls on the site is soaking into these areas and helping to grow stuff. At this point, it's a lot of annuals that are not the most desirable, but it's actually growing stuff, which to me is a good first step. And now it's the phase of managing that vegetation to push it more and more to the desired stuff that we want. And then it's not necessarily water harvesting, but I'm a big fan of controlled flood irrigation. And this is a project here in Moab where we essentially designed a small creek system on what was this flat vacant lot. And it gets flood irrigation water from our local creek. And so it goes through and it has pools and riffles and runs and floodplains, and we're able to irrigate the whole site in about 45 minutes with just turning on one valve, and it just fills the whole thing. And it's been a pretty awesome experiment. And this particular property doesn't have any buildings on it itself. What you can see is the neighboring properties. So we don't have sources of roof water runoff, particularly at this specific project, but these types of, if you are lucky enough to have flood irrigation on your property, you can integrate that with your rainwater harvesting, stormwater management. And so now kind of switching gears, I know it's, we're closing in on 8, so I want to move through a few of these pretty quick, just to give some perspective on roof catchment systems. So this is your tanks and rain barrels. The basic anatomy of that starts with your roof, gutter and gutter screens, which are optional, but essentially the gutter screens keep leafy debris out of the gutters, saving some maintenance if you have a good quality one. Then you want to have a debris excluder, and that essentially sloughs off and keeps any leaves and detritus from getting into your water. So that you want to keep the water in your tank as clean and high quality as possible. So having that debris excluder is really key. And then this first flush, it's not appropriate for areas that freeze. I've stopped installing those because often I'm working in climates that freeze, but also it wastes some amount of water. And the premise there is that first volume of water coming off your roof is essentially cleaning your roof and taking any dust, any bird dropping, stuff like that, and like washing most of it away so it's not getting into your tank. And so it's, kind of a judgment call if you want to do that, but again, not appropriate if it freezes, because it leaves a standing column of water in that pipe until that can slowly drain out. And then you have your inlet conveyance. So your water at this point is no debris in it, travels down the pipe, goes into your tank. On the inside, it's good to have what's called a calming inlet, and that's essentially a pipe that goes from your inlet down to the bottom of the tank and has 2 90s. So it goes up so that the water bubbles up from the bottom instead of cascading down from the top, so that any sediment that does get in there and settles out over time, that you're not stirring it all up every time you get a new inflow. And then, you got your tank on something sturdy. That could be gravel, that could be a concrete pad, depending on your needs and your weight distribution. You want to have some way to get into the tank. Most of these tanks come with an access port that you just unscrew, and they're usually 16 or 22 inch diameter, so you can get in there. And then it's got to be vented so that when you go to pull the water out, you don't get a vacuum lock. And these lids on most of the tanks have a vent in them, but I also sometimes include that in my overflow piping to have a vent, so as waters move and just some air can get in there too. And in this case, there's an overflow that goes to a rain garden. And this, at the time that we did this project, they were just planning to fill up buckets, and they had some children's programming, and they were going to involve the kids in helping to be the distribution system to bring the water to the plants. So there's all different types of gutters and downspouts, you know, angle guards. The bottom left picture is really a testament to not use some of the flexible corrugated materials, because they tend to accumulate debris. And if you can look closely at that bottom left, there's a distinctly darker spot and some icicles coming off that kind of bend in that pipe, and it's just over whatever number of years enough stuff got in there that it's clogged it up and turned it into something you got to maintain. So I recommend using smooth walled pipe and generally using rigid pipe when possible, just to minimize some of these sagging and debris collection things. Living roofs, all the rage. Living gutters, not so cool. And so that's just going to be any house that has gutters, it's a potential maintenance issue to just keep those free and clear of debris, and especially if you want to store that water in a tank for later. Here's a couple options of the pre-filters. So the upper left is that debris excluder. It's really nice because it's there, visible. You can put it at eye level or whatever, and it's slanted, so some amount of the debris naturally sloughs off, but you can walk by and see it and say, oh, I gotta clean that off, and tap it off real quick, as just kind of a part of walking by things. And the bottom right is a basket strainer. That's often used for a lot of underground tanks, but it can also be used for above ground, and they sit inside the top of the rain tank, and then the water comes in, like in that last picture here. Ooh, touchy. You could put that basket filter right in there and then have that water come in that way. And it's just, those are kind of two of the most common options. There's some other products available, but those are the two general types of pre-filters. And that's just a really important thing. To good quality water going in is better quality water coming out. And so here's just a couple different tanks. Dry conveyance, essentially this pipe drains dry after the rain is done. So there's no chance of that freezing. In warmer climates, you can do what's called a wet conveyance system, where you use the self-leveling properties of water to actually move water down across an area and back up, but not appropriate for areas that freeze. So I've stopped including that in a lot of my presentations, but just know that that option is available if you're in an area that's not prone to freezing. And then tank types, you know, these polypropylene, sorry, are the most common types, and those ones that are made to be buried, and then all different sizes and shapes for above ground. The bottom right is the USU Moab permaculture campus, where they've got these slimline tanks doing some roof water catchment that feeds into their rain gardens. And so there's a whole range of sizes and volumes and all of that stuff that you can look into to really customize your need. The one word of caution is that if your tank is not rated to be buried, it's not recommended to bury it, because like this upper right tank, those walls are flimsy. They're not designed to have any soil loading on them, where this upper left tank is designed to be buried and has ribs and is engineered to withstand up to 3 feet of soil on it. Then there's also different corrugated metal tanks. They usually have a liner on the inside so that the rainwater is not corroding the metal, but there's a bunch of different sizes and shapes of those. And then you can also make your own concrete or ferro cement tanks. And then there's, especially in larger volumes for some of the bigger commercial projects, there's different fiberglass tanks as well. And tanks can be prettied up in all different ways, made into sculptures, have murals. The bottom right is just a poly tank with some 1x4 or 1x6 wood slats around it and a nice roof, just so it looks a little better and keeps the sun off of that plastic. For underground stuff, again, making sure it's rated to be buried. You got to have your access to be able to get in there and service and maintain it. And you want that above grade, so you're not getting water flowing into it. You got to overflow to daylight, and then you got to bury the bottom of the tank and all of the pipes below your frost depth, and then rated for whatever loads. They do make some that you can drive and park on, and others that you can only pile a certain volume of soil. And if you have high groundwater, you might need to use what's called dead men to like have the prevent it from essentially popping out of the soil due to the buoyancy of that. Some different frost protection. Heat tape is one option, burying stuff below frost depth. Sometimes people just disconnect their system in the winter and direct it straight into a rain garden. So there's pros and cons to all of those, and it's going to be a situational thing. And so here's that examples of just disconnecting these rain barrels and putting that water into the existing stormwater management system or out into a rain garden. And that can be done opening valves or just fully disconnecting them. And there's one that wasn't disconnected, and it actually split at this seam because it was on a north side of a building and just froze and popped the tank open. And same with your fittings, and your outlet valve at the bottom of your tank is generally going to be your most susceptible to freeze damage, and so just pay attention to that. Sorry for and then yeah, the overflow's got to be the same size or bigger than all of your inflow piping, because you don't want to have a big pipe coming in and a little pipe coming out that can't move all the water, and then it backs up or it bubbles out the top. Everything should be screened for vector control, so often just using window screening so that no mice and especially no mosquitoes and other bugs can get into your tank. And then depending on where you are, that might fall into stormwater discharge regulations, so you might be required to do some additional retention on site. But in general, you really want to look at that overflow as the resource it is. Gravity distribution, totally possible to use gravity to distribute your rainwater. The biggest thing is look at these two fittings on the right, and you want what's called a full port hose bib, and that means that the opening is the full size that it says it is, where this is a 3/4 inch fitting, but the opening is only like maybe 1/4 of an inch. And so that right off the bat is restricting your flow. And every time you restrict your flow, you have less pressure to move that water out into your landscape and out to where you want it. And pumps, I'm not going to really get into those in this, that's beyond this, but just some general vector control stuff to consider is that screening for mosquitoes. You really want to exclude light. So if you use some of these IBC totes, it's highly recommended to paint them or put some boards or something around them, because you can see the dark color of that water on the right, and that's a combination of both leaf and organic debris getting in, but then also that light coming in and growing algae that just decreases the system, gunks things up, can have a foul smell, things like that. So just kind of some best practices to keep in mind. And then I think, let's see. And then I often like to think a lot about scaling up. Every single rain garden, every single rain barrel, every rain tank is a really valuable piece of infrastructure for a site and a community. But the real magic, I think, happens when we can start achieving this at scale and getting just hundreds of applications all throughout a watershed. And that takes outreach and education. It takes getting demonstration projects where it starts to just be what people see and notice as they go about their day and get new ideas from. There can be lots of room for neighborhood collaborations, perma-blitzes, neighbors helping each other dig their rain gardens so that it's more fun and more productive. In the past, I've been involved in some bulk purchasing of tanks, because a lot of times the delivery is a big expense. So if one person's getting a tank and paying the full delivery cost versus if 5 or 10 people are getting tanks and sharing that delivery cost, it can really help make some of the tank systems more cost effective. And then there's also just opportunities to get some of these things into our policies and ordinances. It currently is legal to catch rainwater in Utah. I meant to say that earlier, but you're legally allowed to have up to 2,500 gallons of roof water catchment tanks per parcel. And then there's a simple free registration that you would do with the Division of Water Rights that essentially just says, hey, I have 1,000 gallons of rainwater. So there's that. And then a lot of municipalities and water districts are looking at incentives and rebates to actually accelerate adoption of these, because it's been found in a lot of communities that it's actually cheaper to conserve water and get some distributed capacity through these different efficiencies, roof catchment, gray water, whatever, than it is to drill a new well, build a new reservoir, negotiate a new water right from a river that's over allocated, all these types of supply constraints that we're seeing happening at a municipal and a regional scale. And then ability to have technical assistance too, of having trained professionals that can be funded through some of these incentive and rebate programs to go out and help people figure out what to do on their particular plots. And so that's just kind of some of the stuff I've seen of like, how do we take this from my backyard out to the neighborhood and eventually on through the whole city and watershed. And with that, there's another little plug for that gray water webinar. There's my contact info at the bottom, and